In the last video for lesson 8, we will explore a quadratic graph. And we will do so by looking at its graph features. And normally graph features are something that you've seen before, so we're going to be talking about familiar things like intercepts and intervals. But we're also going to be looking specifically at something new called the axis of symmetry and what that means for quadratic parabolas. So hang in there. Let's look at some graphs. I'm going to start by going backwards a little bit and starting with something familiar. Graph A you've seen in the previous two videos. We've seen the data points, but now what I'm actually going to do is look at the graph and get the points from the graph so that we can go ahead and dive deep and explore. So sometimes you'll get the graph and you'll have an incomplete table. So what I'm going to attempt to do now is complete the table. Now that means that I have to look specifically at these points in the graph. So I notice that my 0 is missing for x, and I'm going to look at that domain and see what else is missing. My 1 is missing, my 3 is missing, and my 5 is missing. And so I'm going to look and see where those points are and write the complete ordered pair. So when x is 0, I notice my y is 3. When x is 1, my y is 0. When x is 3, my y is 0. And when x is 5, my y is going to be 8. And so this is something very similar that you're going to go through when you see a graph and you have to get the points from it, because you really don't know if this is a quadratic. Just because it looks like a parabola doesn't mean it is. You actually have to prove it. Anyway, we have our points in our table. Now, one of the things you may notice with a quadratic is that each point is exactly the same distance from the other when it has the same y value. And so what I'm doing right now is showing that to you. So when y is 0, x is 1, and x is 3, they're exactly, those 2 points are exactly the same distance from each other. And the reason that happens in a parabola is because where we have our vertex, in this case our vertex is at x equals 2, y is -1, and it happens to be the minimum point, so the lowest most point of the whole graph, then the vertex is going to be sitting right in the middle of the graph. If I were to draw a line like I did in green, then it would split this graph in exact halves. So I could fold it and my other half would lie right on top of the other one. And this is what we call an axis of symmetry, meaning if you fold this right here, you're going to create two equally symmetrical sides to this graph. And so the points on the other ends are going to be the same distance from each other. So the axis of symmetry running right through the vertex in a parabola is very characteristic of a quadratic equation. And so in here, my axis of symmetry is going to be at x equals 2. Another popular feature of graphs are the intercepts. In this case, my x-intercepts, I have 2 of them, and they lie at 1 and 3. We also refer to them as zeros because one of the coordinates is going to be 0. In this case, your y is going to be 0. I do have one y-intercept, and it's sitting at 0, 3, but a lot of times you may not even have one, right? One thing for you to notice is that the leading coefficient of this equation, even though I don't know, and that's not the purpose of this particular video, what the equation is, my leading coefficient I know is positive because this parabola opens up. Whenever you have a vertex that's a minimum point of the graph, and that means most of your points are going to be lying on positive y's, so your leading coefficient is going to be positive. Now, if this were the other case upside down, and we'll see an example like that in a minute, then it would be a different story. And we'll look at those points. But in here, the only negative that you have is that -1. Everything else in this graph is going to be positive. So we call this graph a positive graph with a leading coefficient that's positive. So far, we have looked at our vertex, our intercepts, our axis of symmetry, our leading coefficient, and identified that this is a positive quadratic parabola. Now let's look at intervals. In this particular graph, we have a decreasing interval and we have an increasing interval. Now, intervals, as you know, we refer to them using x values only, and intervals are just portions of the graph that move in the same direction. And so in this case, whenever we read the graphs, and all graphs are read from left to right, we notice that our decreasing interval comes first. And we start seeing this decreasing interval at -1. However, we know that this graph keeps going up. And so we know that there's other values that we are just not able to see in the graph that are part of that decreasing interval. So that's why we're going to start naming this interval with a negative infinity, assuming that it's starting anywhere in x equals negative something. So it starts at negative infinity and it goes down, down, down all the way to the vertex. And the vertex is lying at x equals 2. And that is the decreasing interval. Because once it gets to x equals 2, anything above that is going to be part of an increasing interval. It's going to go in a different direction. So that portion of the graph is going to go up. So our increasing interval is going to be starting at x equals 2. So we're going to start this at 2. And it's going to keep going up, 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 presumably an infinity above to a positive infinity. And that's how we're going to define this interval. Now let's look at a parabola that looks a little bit different and try to identify the graph features for that one. You have seen this before. This is graph B. We've used in other videos. And I'm first going to get the points from the graph into my table. So I'm identifying there part of the domain that is missing. I've written it down, and now I'm going to look at where those y, where that range is for those particular values. So when x is -5, y is 5, and I'm going to fill my table before I start identifying graph features. Initially, the easiest thing to identify are the zeros, because wherever you see zeros, those are intercepts. So if y is 0, those are going to be x-intercepts, and if x is 0, you're going to be looking at a y-intercept. So in this particular case, it's interesting because I have only 2 zeros, but there's 1 0 that doubles up. So I have 2 x-intercepts, and one of those x-intercepts also happens to be the y-intercept. And I'm talking, of course, about the origin there. It crosses both the x and the y-axis. So even though I'm labeling here x-intercept, you know it's also considered the y-intercept. The graph doesn't really cross the y-axis at any other point other than the origin as well. Now let's see if I can identify the vertex. And here I see that my vertex is lying at the -2, 4 ordered pair. And what's different about this particular vertex is that it is actually the maximum of the graph, so it's the highest most point, not the lowest. That means that this graph is going to be facing down. And so we're going to call this graph negative because most of the y values in this graph are going to be negative, and we're going to assume that it also is going to have a negative coefficient because of it. Now, once I identify my vertex, I can look for my axis of symmetry, and that is the line that's going to cut through this graph right in the middle. And my vertex is at x equals -2, and so that's where I'm going to draw my line at x equals -2. And that is going to be my axis of symmetry. So basically, every point on this graph who shares the same y value is going to be the exact same distance from the axis of symmetry. So look at your intercepts, for example. Your intercepts are at -4 and at 0. And if you were to count how far away they were from the axis of symmetry, they would be 2 units away. And so you can grab any point on this graph that is sharing the y value. They're going to be, it's going to take them the same amount to get to the axis of symmetry from each other. So it's super useful to know where your axis of symmetry is. Sometimes you won't get graphs that are showing every single point like this graph, for example, and you will need to draw the missing point. Well, if you have the opposite point, then you can count from the axis of symmetry to the opposite end and get the next point. So axis of symmetry is actually really quite useful when you are trying to solve problems that involve a graph and you don't have the entire graph. All right, so let's look at our intervals. In here, if I'm reading the graph from left to right, I'm going to have an increasing interval first. And I'm going to presumably say that this starts anywhere from negative infinity, x is negative infinity, all the way up to my vertex. And my vertex is as x equals negative 2. So my increasing interval here is negative infinity to negative 2. Now once you get to negative 2, then it starts going down. So that would be a decreasing interval. Your decreasing interval, negative 2, all the way to a positive infinity. And those are pretty much the most important graph features for a quadratic equation. In class, you're going to get to do some exercises to identify these graph features, write equations. So all these 3 videos are going to be really useful for you. Feel free to watch them again, look at the quiz questions, and watch them again if you need to help you answer them.